Welcome to this explainer. We often look at math as just, arbitrary rules or abstract puzzles we're forced to solve in a classroom. But what if we flip that perspective? Today, we're going to see how mathematical concepts are actually the essential foundational language we absolutely need to read, write, and truly understand the laws of our physical universe. If you've ever stared at a dense physics equation and felt totally lost, hey, you're not alone. But once you see it as a language, it's a real game changer. Our syllabus today covers 4 quick steps. 1. The basic grammar of algebra. 2. The spatial vocabulary of trigonometry. 3. Visualizing math through graphs. And 4. The dynamic syntax of calculus. Let's get right into it. The source text we're analyzing today anchors our whole journey with this brilliant metaphor. It reminds us that to grasp the mechanics of the universe, to figure out why planets orbit or how forces interact, we first have to learn the language it speaks. I mean, you can't write a great novel without knowing verbs and nouns, right? Well, you can't express physics without math. Sir Isaac Newton hit the nail on the head with this. He didn't just casually observe gravity, he used the exact mathematical symbols of his era to unlock, define, and literally write down the greatest physical discoveries of his time. Mathematics was his ultimate translation tool. So, Section 1, Algebra, the basic grammar. Let's dive into our first lesson. Think of this as your basic nouns and verbs. Mastering core algebraic progressions and equations gives you the fundamental structural tools you need. Whether you're working with quadratic equations, the binomial theorem, or arithmetic and geometric progressions, these are the actual mechanisms that allow you to solve for unknown variables. They give real structure to physical relationships. And what's really cool is how we apply these tools in different contexts. Take the quadratic formula. It provides your exact roots. But the binomial theorem, that acts as a crucial grammar shortcut. When you're dealing with teeny tiny values, like calculating the very slight change in gravity just a short distance above the Earth's surface, the binomial theorem lets you strip away the insignificant fractional variables that would otherwise make the math impossibly tedious. It dramatically simplifies complex equations without losing any meaningful accuracy. You get clean, workable numbers in seconds. Moving right along to Section 2, Trigonometry, Angles, and Space. To describe the 3D world around us, we really have to expand our vocabulary. And this simple right-angled triangle, it's our Rosetta Stone for space. It defines essential terms like sine, cosine, and tangent, just based on the relationships between the hypotenuse, the perpendicular, and the base. Anytime you're dealing with angles, forces pulling in different directions, or flying projectiles, this triangle is your go-to translator. Memorizing the standard values for specific angles like 0, 30, 45, 60, and 90 degrees is exactly like learning everyday conversational phrases before traveling to a new country. It equips you to effortlessly translate and solve spatial problems involving trajectories and vectors, completely saving you from having to derive the basic logic from scratch every single time. Okay, Section 3, Graphs, Visualizing the Math. We've got the written grammar down, so now let's transition into visual communication. Graphs actually take equations and give them a physical shape. A straight line represents a constant rate of change. Picture a car cruising at a perfectly steady speed. Meanwhile, the symmetric curve of a parabola visually communicates something totally different, like the acceleration of an object or the arc of a baseball flying through the air. You can literally just look at the shape and instantly know what kind of physical motion is happening. Building on that visual momentum, we see circles and ellipses. These are the specific visual shapes physics uses to describe bounded, recurring paths. This could represent everything from the microscopic edge of a spinning wheel here on Earth to the massive, literal elliptical orbits of planets cruising around the sun out in the cosmos. And when we look at periodic sine and cosine curves, we see something truly brilliant. If you take that right-angled triangle from trigonometry and sort of stretch its changing angles out over time, you get these visual tools. They perfectly capture the continuous, repeating rhythm of sound waves, light, and alternating currents. Finally, Section 4, Calculus, the math of change. If algebra is our basic grammar, calculus is the advanced syntax required for our final lesson. To describe a universe that is in a state of constant motion, flux, and change, the crucial point is understanding the two sides of the calculus coin. Differential calculus breaks things down to find an instantaneous rate of change, like glancing at your exact speed on a speedometer for one split second. Integral calculus does the exact reverse, summing things up to find a total accumulation, like the total distance you've traveled over a shifting and changing road trip. Differential calculus is incredibly practical. Imagine you throw something straight up into the air. It travels up, slows down, stops for a fraction of a millisecond, and then falls back down. By finding where the rate of change is exactly zero, that perfectly flat line right at the peak, we can mathematically pinpoint the precise maximum or minimum limits of any physical scenario. So, how do we find the exact time a thrown ball reaches its maximum height? Let's test our new language fluency with this classic real-world physics problem outlined in our source text. How do we pinpoint that absolute peak moment? Using our calculus syntax, it takes just 3 simple steps. First, we write the basic algebraic height equation. Second, we use differential calculus to find its derivative, which gives us the rate of change. And third, we simply set that rate to 0. By doing that, boom, the equation instantly reveals the exact time the object reaches its peak. It's elegant, it's incredibly fast, and it perfectly translates the physical world into a solvable sentence. Mastering this exact mathematical language is what ultimately allowed Newton to write the Principia Mathematica. He didn't just guess at how the universe worked. He translated the raw, invisible mechanics of reality into a structured, readable format that humanity could finally understand and utilize to build the modern world. Which leaves us with this final, provocative thought to take away. We humans consider mathematics to be a language that we invented. But if we invented this language, why does the entire physical universe seem so perfectly fluent in it? Definitely something to chew on. Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you next time.